Okay, so we're back here with number 13 up here. There's a little bit of a glare here, but this is a -3 behind there. I don't know if you can see it. Okay, so number 13 suddenly looks a little bit more complicated, but we're just going to take it one step at a time. Any of these problems is really just a combination of those different rules put together, one way or another. So, and as I said, we always want to take care of the parentheses first. So I'm going to go through and multiply these outside exponents by every inside exponent. And I would suggest literally going through and putting in a 1 on any number or variable that does not have an exponent. Okay, it will save you from making mistakes along the way. So, I'm going to see if I have a better marker here for that. Not that one. All right, so if we look at the top, we want to take that -2 and multiply it by all of the exponents in there. So I'm going to have x to the -2nd, y to the 6th, y to the -6th, z to the 4th. Okay, multiplied -2, -2, -2. Now I look at this part right here, and I see this 0, and anytime you see a 0 as an exponent, you need to kind of have that, send an alarm bell off in your brain. So this whole thing is being raised to the 0 power. That means this whole thing just equals 1. I don't really need to write it there because I have something else that's going to be here, not just a 1, but I just want to put it there for clarification. Now, if you forget that and you say, oh, I'm just going to multiply this, you would get 3 to the 0, x to the 0, y to the 0, which again would all be 1 anyway. Okay, but try to train yourself that every time you see that 0, you really think about what's being raised to the 0 power, what is it that's going to equal 1. In this case, this whole thing equals 1. Then over here, I have 2 to the -3, x to the -3, y to the -3, z to the -12th. Okay, now again here, I could move things around so that everything has a positive exponent, and that's perfectly fine. And I'm going to kind of take this away right now, right, to make it a little easier, because 1 times this whole thing is just going to be this. Let me do an example of not moving things around. You can do that. Just, again, be very, very careful with your exponents with the quotient rule when they're negative. So, for example, I'm just going to leave this 2 to the -3rd down here for now. So I have x's. I have this and this. So, for my x's, I have -2 minus -3. That's the same as -2 plus 3, which is going to be 1. So I'm going to have x to the 1st power. When I take top minus bottom, it always ends up on the top. Now I'm looking at the y's. So for y, I have -6 minus -3, or -6 plus 3, which is -3. So y to the -3rd. And then z, I have 4 minus -12, which is the same as 4 plus 12, which is 16. So now let's move things around so that they're positive. So the 2 is actually going to go up on top. So 2 to the +3rd, x and z to the 16th are going to stay on the top, and y is going to go to the bottom to be a +3rd. Okay, so that was lots of practice there. Hopefully you started feeling more comfortable with those exponents. And if you need more practice, also there are videos on Lumen with, the videos that are right from Lumen with the practice questions. And of course, obviously, there's also homework, all right? Also, if there's anything on there that you weren't sure about, make sure that you email me or stop into office hours. So my office hours, I had some today, but I also have some Friday or by appointment. Just email me and we can set up I can help you by email, or we can set up a time for a Zoom meeting to help. Okay, so the next page is scientific notation. So I'd like to talk about that next. So scientific notation, we know, is a way to write very large or very small numbers in a compact way. So if you're working in science, you're looking at astronomy and the distance between stars, or you're looking in finance, countries' budgets that are in the billions and trillions, or if you're looking at cellular distance is. Very, very, very small. So those numbers, they have a lot of place values, either after the decimal point or before. It gets a little bit unwieldy. So scientific notation is a nice way to sort of write things compactly. This is usually a topic people remember a little bit. Okay, so we write it in this format. This is going to be a number. I'm going to just say, just kind of a simple way, is between 1 and 10. Now, if you look at your notes, it says A has to be like this, right? So if we think back to what this means, it means A has to be greater than or equal to 1, but less than 10. So it can't actually be 10. It has to be like 9, but it could be 9.9999999. It can't actually be 10. In other words, this has to have one digit in front of the decimal point, 9 point something or 7 point something. It couldn't be 17 point something. And then N is the exponent here is an integer. Okay, which means if we think back to the very beginning of the semester when we talked about number sets, an integer can be positive, it can be negative, it can be 0. It does not have decimals, it does not have fractions. Okay, so let's think about kind of some powers of 10 first. So we're going to think about 10 to the first all the way up to 10 to the sixth. So 10 to the first is just 10. 10 to the second, we know that means 10 times 10. 10 multiplied by itself 2 times is going to be 100. 10 to the third multiplies by 10 again is going to be 1,000. Okay, and so on. So 10 to the fourth is going to be 10,000. 10 to the fifth, which again we'd get by saying 10 times 10 times 10 times 10 times 10 is 100,000. And then 10 to the sixth is 1,000,000. Okay, so when we talk about powers of 10, sort of the easy, simple way to say it, which I fall into this trap too, is kind of to say, well, we just add a 0 at the end, right? But really what we're doing is we're not really adding a 0 at the end. If you think about this is the ones place, and this is the tens place, and this is the hundreds place, if I start out here and I multiply it by 10, I'm not really adding something to the end. What I'm really doing is moving everything up one place value, because a 10 times 10 becomes 100, and a 1 times 10 becomes a 10. Okay, so I fall into the trap of saying, oh, we move we add a 0, or we move the decimal point. We'll talk about that. But really, we're moving all the place values up. Okay, if I multiply by 1,000, I'm going to move everything up 3 places, because this would be times 10, this would be times 100, this would be times 1,000, because our place value system is all based on tens. Okay, so let's look at the powers of 10 that have negative exponents. And again, I'm going to go from -1 down to -6. All right, so think about what we just learned with negative exponents. 10 to the negative first is 1 over 10 to the positive first, or just 1/10. So 1/10 of something is smaller than that whole thing, right? If I have a candy bar and I give you 1/10 of my candy bar, that means I split it into 10 pieces and I'm giving you just one of them. 1 over 10 squared would be 1 over 100. 10 to the negative third is 1 over 10 to the positive third, which is 1/1000th, and so on. So we see this pattern. Okay, and every time that we go down in this row, so our integers here are actually getting smaller, our number gets smaller also. Okay, so we said at the beginning, 1/10 means I'm going to break my candy bar into 10 pieces and give you one of them. Down here, this is 1/1,000,000th. This means I'm going to break my candy bar into 1,000,000 teeny tiny pieces and give you one. That's way smaller than that, right? So if I take a number and I multiply it by one of these values, it's going to make it smaller. If I have $5 and I give you 1/10,000th of what I have, it's going to be a tiny, tiny little amount of money. If I take my $5 and multiply it by 10,000, that's going to be a really big amount of money. So sometimes when people learn scientific notation, they've learned to sort of memorize when you go left and when you go right and what's positive and negative, and I don't really like that because when you just memorize things, it's easy to forget it and then you have no backup. But we're going to think about this, that 10 to a positive exponent gives you big numbers. And I'm just talking about big being anything greater than 1. And 10 to a negative exponent gives you little numbers, okay? These can also be written as decimals. So 1/10 is going to be 0.1. 1/100th is 0.01, right? 10ths, 100ths, this is a 100th. And etc. So it keeps moving over one more place value. Okay, so you can see that they're really small pieces. So if I take something and I multiply it by one of these, it gets smaller. And these are small numbers, smaller than 1. Okay, so let's do the first example. It's what do we have here? 540 million. And I want to write it in scientific notation. So I want to write it in such a way that I have some number times 10 to some power. Okay, I'm going to fill in those two boxes. This number has to be between 1 and 10. So when I have a whole number, my decimal point is kind of hiding out back here. I'm going to move that decimal point. Again, that's kind of a lazy way of saying it, but another thing you could think of is I'm going to shove this whole number over until I have a number between 1 and 10. In other words, I have a number where there's only one single non-zero digit in front of the decimal point. So if I move this over, if I move it to here, I still have 54 million. That didn't get me where I needed to. So I'm going to keep moving it until I get to right here, because now I have 5.4 with a bunch of zeros after it. But zeros after the decimal point, after the last number, don't matter. So my number now here is 5.4. Okay, now we know that 540 million is not the same as 5.4, obviously, right? If I have $5.40, that's not the same as $540 million. So what's going to make the difference is this 10 to some power over here. So together, these two would give me the number I started out with. So I want to see how many times did I move that decimal point over, or how many times did this number get shoved over. So I moved it over 1, 2, 3, 4, 5, 6, 7, 8. So I know right now that my exponent is either going to be 8 or negative 8. Well, the way I know is by whether this is a big number or a small number to start out with. My 540 million that I had to start out with, that's a big number, right? So 5 has to get multiplied by something big to make this big number. 10 to the 8th power is going to be 100 million. So 5 times 100 million would be 500 million. And then this little 0.4 gives me that. So if your number in what we call standard notation, regular old number, is bigger than 1, then your exponent's going to be positive. Let's look at the next one. The next one is 3,783,000,000. Okay, again, my decimal point starts out hiding over here. I move it over until there's just one number in front of the decimal. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to have 3.783 times 10 to the 9th. I know this is going to be positive because I have to multiply 3 by something really big to get this really big number. Okay, I'm going to stop this video and I will be right back with the next page on scientific notation.